Okay, so I had a few questions. So I've added this red box on the slide because I was asked what the electric field is. In Maxwell's theory, if you took the ith component of the electric field, this would just be the naught I component of the field strength. It's exactly the same in the non-abelian gauge theory, except if you want the ith component of electric field A, that'll be the naught I component of the A field strength tensor. Then the other question I got, I was asked, what is epsilon ABC? Well, epsilon ABC is defined like this. So epsilon ABC is totally antisymmetric. So I'll get a minus sign if I swap B and A. Uh, and I'll get a minus sign also if I swap C and B. So just a minus sign if I swap any two indices. And I also specify that epsilon 1, 2, 3 is equal to 1. So let me give you an example of getting a value. So let's say that we wanted to work out what's the value of epsilon 3, 2, 1. Well, this will be minus the value of epsilon 3, 1, 2. I've swapped the 1 and the 2. And this will be the value of epsilon 1, 1, 3, 2. And this will be minus the value. So here I've just swapped, what did I swap? I swapped 1 and 3. And now this will be minus epsilon 1, 2, 3. So this is minus 1. Good. Okay, so now let's try to solve this. In my discussion below, I'm going to try to draw some pictures. So let me tell you the color coding for my pictures. So I want to solve this equation of motion. From now on, whenever I want to describe A is equal to 1, I'm going to use black. So all of the 1 fields will be drawn in black. Whenever I want to draw A is equal to 2, I will use blue. So all of my 2 fields will be in blue. And whenever I want to draw A is equal to 3, this will be drawn in red. Good. So let's imagine that I want to switch on a 1 charge. So let's consider an E1. Okay. So how do I switch on this electric field? Well, my charge density, so rho A of x, I'm going to say that this is equal to delta A1. So it's only non-zero if A is equal to 1. And then I've got a delta of x. So I've got a charge sitting at the origin. And then I will say that JA is equal to 0. So there's no currents. I've got some charge density, but it just corresponds to a type 1 charge sitting at the origin, just a static charge sitting there. So I need to solve this equation of motion. How does it differ to Maxwell's equation? Well, it's the second nonlinear term that I have to worry about. But notice that I've only got a charge of the 1 type of electric field. So I'll switch on a 1 electric field. I'm not going to switch on a 2 electric field or a 2 gauge potential at all, so that B and C can only possibly be non-zero if B is equal to C is equal to 1. But as soon as 2 indices of the epsilon are equal to each other, it's 0. So right now, I don't even have to worry about that nonlinear interaction. It's not going to play a role at all. That nonlinear interaction term vanishes. So I'm back in the realm of usual electrodynamics. The equation, because as soon as the nonlinear term is gone, it's just like I'm solving the equations of electrodynamics. Okay, so what does the electric field look like? Well, it's going to be just the usual Coulomb field, okay? So it'll have the usual 1 over r squared fall off. It'll point radially outwards. It will be exactly the Coulomb field that you are used to. But I'm interested in this nonlinear term. That's actually what I'm interested in. To see that nonlinear term, I need to let the vacuum fluctuate. So let's say let the vacuum fluctuate. And the way that I'll do that is I'll imagine that there is a fluctuation of the gauge field. So I'm going to call that delta A for the fluctuation. So the delta is meant to just remind you that it's a fluctuation. And I will let the 2 component of the fluctuation vanish. Now, when I said I was going to draw the solution, this is what I mean. I will have a fluctuation at this region over here. This is my delta A2. So what I want to know now is, what does this nonlinear term in the equation of motion do? So let's just pick it up from here. We'll write it below, and let's just see what does this nonlinear term become. Okay, so we'll put it there. Good. And what do we want to describe with this nonlinear term? Well, we want to describe this fluctuation, the delta A2, with this E1 field. So what do we get? Well, this is equal to, we will have our E sitting here. Oh, no, that's fine. Good. We will have this E sitting here. And B is summed over, but the only uh, gauge field, the only gauge boson that's non-zero is the 2. So I'll have an A, then I'll have a 2, and then so I've got delta A2 sitting here, and then this is dotted into the electric field, but the only non-zero electric field is the E1. So I'll have a 1 sitting here. Okay. So I've just plugged in now the non-zero gauge potentials and the non-zero electric field. Now, the epsilon tensor vanishes if any 2 indices are equal. So I'm going to get a delta A3. A has to be 3 to get a non-zero answer. If A is 3, we've got epsilon 3, 2, 1. And we just evaluated epsilon 3, 2, 1 and found out it was -1. So we'll get a negative sitting over here. And then let's imagine that the angle between this potential and this electric field over here, let's call it theta, it's less than 90. So we will have a mod of delta A2 dotted into E1 and a cosine of theta. And because the theta is less than 90, this cosine theta will be positive. And we know this magnitude will be positive. So what do we have now? It looks like we've got a negative type 3 charge sitting where this blue A field line and the black E field line are interacting. So now what we'll do next is, let's calculate what this negative source of the 3 field does.